Here we come. The third category, which is also the last category of calculations of this chapter, calculations based on chemical equations, which is also called stoichiometric calculations. Basically, using chemical equations to relate the masses or moles of number particles of the substances in the chemical reaction. No surprise, this is the flow chart we're going to use, giving information for any one substance. For example, if we know grams of one substance, we can convert the grams of that substance to moles of the substance. Then, by using the equation coefficients, we can convert the moles of the given substance to the moles of any other substances in the equation. Then, depending on what information is wanted, be it moles or grams or particles, you can convert from there. Make sure, before you do calculation, make sure the equation must be balanced. Okay? Only the balanced equation have the correct molar ratios. If the mass is what is given, then you convert known mass of the reactant or a product, whatever is given, to the moles of that substance. Then using the balanced equation to set up the appropriate molar ratios to convert the moles of that substance to the moles of another substance. And then if the mass is wanted, you convert from moles back to grams. That's what we just discussed on the last slide. Grams to moles, moles to moles, moles to grams. This is what the above procedures is talking about. All right, practice. Since a balanced equation is required before you do any calculation on it, so let's practice writing out some balanced equations. Write balanced equations for each of the reactions below. The first reaction, methane reacts with oxygen in the air to produce carbon dioxide and water. All right, the reactant is methane and oxygen. Oxygen is O2. The molecular formula for oxygen is O2. The product, carbon dioxide and water. They are provided from the statement to produce carbon dioxide and water. Okay, we'll focus on the hydrogen first. For the 2 here, hydrogen is balanced. Now look at the oxygen, or carbon is balanced, oxygen balanced. This is the balanced equation for the first reaction. The second reaction, ammonia reacts with oxygen in the air. Again, ammonia reacts with oxygen in the air to produce nitrogen monoxide plus water. Now balance it. Let's balance the hydrogen again. Put the 2 here, put the 3 here. Hydrogen is balanced. Then nitrogen, put 2 here. Well, if you look at the oxygen, there are 5 oxygen on the right. You need a 5/2 here. Again, we cannot use fractional numbers, so let's multiply everything, all the coefficients by 2 to eliminate the fractional number. Multiply each one by 2 is going to be 4, 5, 4, 6. That will be the balanced reaction for the second reaction. All right, we have the 2 balanced equations here. Let's look at what is the question now. What mass of ammonia would produce the same amount of water as 1.0 grams of methane reacting completely with oxygen? Wow, wow, wow. What is it asking us to do? Well, looks like methane reacts with oxygen. Methane reacts with oxygen, will produce water. Ammonia reacts with oxygen, also produces water. Now, the question tells you you have 1 grams of methane react completely with oxygen, it will produce certain amount of water. Then it is asking you for the second reaction, if it will produce the same amount of water, like that one, how many grams of ammonia is needed? Clear? All right, how many grams of ammonia, the mass ammonia, would produce the same amount of water as 1 grams of methane would when it reacts with oxygen? Okay, so what we will do is that we're going to use the first reaction to figure out how much water will be produced from 1 grams of methane. Once we know that, we will use the second reaction to see to produce that amount of water, how many grams of ammonia is needed. All right, so let me erase all of this. Let's start our setup. Our job number 1 is to go from grams of methane to amount of water. So we are going from grams of methane, grams of something A. In this case, right now, for the first part of the question, A is methane. We know grams of methane. We're going to go to amount of water. Amount of water could be moles of water, grams of water, particles of water. Which one? Either one. Let's stop here because here we need fewer conversions. Let's figure out how many moles of water can be produced from 1 grams of methane. A is methane in this case, B is water in this case. So we're going to go from grams of methane to moles of water. Looking at the flow chart, you know you need 2 conversions. The first one will go from grams of methane to moles of methane. The second one will go from at the bottom, from moles of methane to moles of water. Okay, A is methane, B is water. All right, let's add the numbers in. Starting point, we have 1.00 grams of methane. What is this? The flowchart tells us this is the molar mass of methane. Let's use 12.0 for carbon, 1.0 for hydrogen, and that will give us 16.0 grams in 1 mole of methane, molar mass of methane. What is this conversion factor then? These are the equation coefficients. In front of the methane, the coefficient is 1. In front of the water in the equation, the coefficient is 2. The setup is done. Do the calculation. You're going to get 1/8 moles of water. When 1 grams of methane reacts with oxygen completely, it will produce 1/8 moles of water. Now let's move on to the second part of the question. To produce 1/8 moles of water, how many grams of ammonia is needed? Now this time we know moles of something. Let's say we're still here. We know moles of water. B is water right now. We want to know grams of something else. Grams of A. We want to come here. Okay. In this case now, for the question number 2, A is ammonia. We need to know grams of ammonia. That is what is asked. All right, So let's start setting up. Again, I'm going to erase all of this to make some room for ourselves. And let's start the setup. We start with moles of water. We know moles of water. We want to convert it eventually to grams of ammonia. From the flow chart, we know we need two conversions, one from moles of water to moles of ammonia, two from moles of ammonia to grams of ammonia. So from moles of water to moles of ammonia. The second one from moles of ammonia to grams of ammonia. Starting point 1/8. Molar ratio of the two, looking at the coefficients. In front of the ammonia, it is 4. In front of the water, it is 6. In this case, we're using the second equation. What is this? This is the molar mass of ammonia. It is going to be 17.0 grams over 1 mole. You do the calculation, 68 divided by 48, you're going to get 1.42 grams. It's going to be 1.41 something, but initially here you have 3 sig figs. You're going to keep 3 sig figs here, 1.42 grams of ammonia. All right, 1.42 grams of ammonia is needed to produce the same amount of water as 1.00 grams of methane. If you need more practice on the calculations on the chemical reactions, there are plenty in the book, in the end of chapter questions. You can find them online as well. Just try to make sure you follow the procedures, stick to the flow chart, keep doing the same thing, you will become really good at that. Now we come to the final topic of this chapter, the percent yield. The percent yield is the ratio of the actual yield of a product to the theoretical yield. So this is the formula how you get the percent yield. However, what is actual yield? What is theoretical yield? Well, theoretical yield is the so-called calculated yield. It is the amount of a product calculated based on the chemical equation, or using the chemical equation, given the amount of the reactant, calculate how much product could have been produced based on the equation. That's called the theoretical yield. The actual yield is the amount you actually get in the lab. If you perform a chemical reaction, you'll know there's no way you're going to get the exact amount as the one calculated. So the actual amount you get divided by the calculated amount converted to a percentage by multiplying 100, that is called the percent yield. Well, let's do a practice. When 14 grams of carbon monoxide reacted with oxygen, and here's the reaction, 18.7 grams of carbon dioxide are obtained. Okay, you do get this much carbon dioxide when you perform this reaction. What is the percent yield? All right, what is that number? Is that actual yield or theoretical yield? Of course, it is the actual yield. That's what you get. So in order to get the percent yield, you will need to calculate how much of carbon dioxide could have been produced from 14 grams of carbon monoxide. In other words, you need to calculate the theoretical yield before you calculate the percent yield. So let's do it. Okay, let's use our flow chart again. What do we know? We know grams of carbon monoxide. We know grams of something. Grams of carbon monoxide. This is what we know. A, in this case, is carbon monoxide. We want to know how many grams of B theoretically that could be produced, the grams of carbon dioxide that could be produced theoretically. So we're going to go from grams of carbon monoxide to moles of carbon monoxide, moles of carbon monoxide to moles of carbon dioxide, moles of carbon dioxide to grams of carbon dioxide, grams of carbon monoxide. Eventually, we're going to get grams of carbon dioxide. We need 3 conversion factors. So there's 1, 2, 3. We need 3 conversion factors. The first one goes from at the bottom, grams of carbon monoxide, to 2 on the top, moles of carbon monoxide. By the end of here, we're here. Next, from moles of carbon monoxide, from at the bottom, to moles of carbon dioxide, moles of carbon dioxide. By the end of here, we're in this box. Last one, from moles of carbon dioxide, again from at the bottom, to 2 on the top, grams of carbon dioxide. This will be the final setup. Let's put the numbers in. We have 14 grams of carbon monoxide. Now, this is going to be the molar mass. The molar mass of carbon monoxide, 16 plus 12, which is going to be 28.0 grams in 1 mole. And this will be the molar ratio from the coefficients of the equation. In front of carbon dioxide, we have 2. In front of the carbon monoxide, we have 2. And the last conversion factor, the last one, will be the molar mass of carbon dioxide, which is 44.0 grams 1 mole. Okay, let's do the calculation. It's going to be 14, 28, 28 to 88, 22.0 grams of carbon dioxide. Theoretically, you're going to get 22.0 grams of carbon dioxide. So percent yield is the actual yield, which is 18.7 grams given in the question, in the original question, divided by the theoretical yield, which is what we just calculated, 22.0 grams. Convert it to a percentage, which is going to be 18.7 divided by 22. That will be 85.0%. So the percent yield of carbon dioxide is 85.0. All right, that's it for today, and that's the end of this chapter.